So let's talk a little bit more about the resting potential, okay? This is going to be a term that will confuse you at first, but it'll make sense as we continue. I want you to sort of dissect this term. Resting potential. Resting means the neuron is at rest, which means it's not sending an action potential. It's not sending a current. It's not communicating in the sense of sending some charged, set of particles from one end to the other, okay? Potential actually refers to the difference in charge across the membrane. Now, what I've been describing are a number of charged substances, right? Potassium, sodium, anions, or those proteins. They are distributed across the membrane. And there's going to be some unequal distribution of these charges across the membrane. There are going to be, for example, more sodium ions on the outside in the extracellular space, right, because of that pump. There are going to be more potassium ions on the inside, right, because, again, of the action of that pump. There are going to be more of those negatively charged anions, right, on the inside because they are proteins and they are manufactured inside the cell, right? So the resting potential difference, that's what you should read it as. It's the difference in charge distribution, difference in charges, on the inside versus the outside when the neuron is at rest, okay? So let's look at our, membrane again. So this is a chunk of membrane, right, of a neuron. We have our phospholipid bilayer that's located right here, right? It's largely impermeable, doesn't let charged things go through. But we have a lot of different, channels that do let things go through. We have, some potassium channels that are open and ungated, right? Which means that potassium can go from one end to the other, right? And we also have very few, but some, ungated sodium channels that allow sodium to pass from one location to another. And we also have our pump, right, which is kicking the 3 sodium out every time it brings 2 potassium in, okay? And again, we have the proteins, so the anions that are located inside. Now, you'll note that potassium seems to be flowing out, right? If you look at this arrow, this indicates the direction of flow, right? And you'll notice that sodium appears to be coming in, right? Well, what is provoking the movement, of these ions? Why are they moving from one side of the membrane to the other? What sort of drives their, their direction of movement? Again, if we're going to be describing neurons as carrying electrical currents, we have to understand that a current, an electrical current, is the movement of charged particles. So already you can see these little localized currents. Potassium's going to be moving out, sodium's moving in. What drives them? Well, let's look. It turns out that 3 distinct forces act on ions and determine, their general direction of movement, okay? The first force that you need to know is the electrical force, sometimes called the electrostatic force. And this is sort of the classic idea that opposite charges attract, right? And like charges repel. So if something is positively charged and nearby is something negatively charged, they're going to move towards each other, right? They attract each other. That's the electrical force. If something is positively charged and it's near something else that's positively charged, it'll try to move away, right? Because this is the repulsive force of like charges, right? Like charges repel each other. So that's one, driving sort of force. So if I were to tell you, looking at this, membrane here, right, that because of this pump, right, which is kicking out, all this sodium, 3 sodium for every 2 potassium that come in, right? Well, we're setting up a difference here, aren't we? Because we're taking 3 positive charges and sending them outside for every 2 positive charges we bring in, right? So we're actually putting more positive charge on the outside. So the resting potential is going to be, involve more positive charges on the outside or extracellular space versus the inside or intracellular, part of the neuron, right? So if you have all this sodium that's out here, right, and it's in a positively charged environment, and the internal space is going to be more negatively charged, well then I want you to think about which direction the electrical force will try to drive sodium. And the electrical force is going to be contributing to the fact that sodium is moving from the outside into the cell.